Hi everyone, and welcome to our webinar today. I'm going to hand it over to Greg and Steve to take us away.
Hi, I'm Steve Glennon from CableLabs, joined by Greg White. We're both distinguished technologists, and we have spent about the last 4 or 5 years working on trying to improve legacy and jitter in computer networks. So if we switch to the slides.
Yep.
So I wanted to give a brief introduction to CableLabs. You may have not heard of us. If you go to the next slide here. We're basically a small company, about 200 people, but we're kind of at the center of the worldwide cable industry. We work on developing specifications for the benefit of the cable industry to help get interoperability and improve services. The industry that we serve and that we're funded by is about $450 billion. We have a whole bunch of patents. We have about 200 subscribers that are served by our member companies. And that leads us to touch the lives of about 500 million people every day. We also focus heavily on bringing new technology and startups into the cable industry. So we've introduced about 500 startups into the cable industry, trying to bring their technology for the benefit of cable subscribers. We have a wholly owned subsidiary, Curio, that does testing services, and we've invested about $23 million in test equipment for that purpose. So moving to the next slide here. Forgive the graphics here, you know much of this, but I want to explain why is the gaming industry important to cable. So you probably know a bunch of this. The gaming industry is larger than the movie and music industries put together. And it's mainstream for the kind of the sweet spot of cable subscribers, millennials and Gen Z. Gamers are using a lot more data in general than your typical household. So we want to make sure we're providing premium service, an excellent, outstanding service to them. And gamers typically choose our higher speed tiers because they understand the value of their broadband networks and they want to make sure they have a great service. But gamers are also very intimately familiar with their ping time. They understand that latency is a topic and that jitter is a hot topic. So this is like a very well-informed population that understand some of the characteristics of the network. We need to make sure we provide a great solution for that demographic. So on to the next. So we've done a whole bunch of primary research. We don't presume to know everything. So we've done a bunch of primary research. And what we found is that gamers have very, very targeted pain points around network behaviors. The typical thing we see is you're playing an online multiplayer game. Here we've got League of Legends. Everything's going great, responsive. You're playing with your team of friends. But then someone else in the household decides they're going to watch streaming media. So they fire up something and suddenly the ping time has become very erratic. You're missing shots, you're getting shot, and you're let down to your team on the game. So we heard this loud and clear in our primary research that this was the typical scenario. So we wanted to start to dig into what are the issues that cause this and what can we do about it to improve the characteristics. So with this, I'll hand it to Greg to tell you a little bit more about that.
Sure, thanks, Steve. So one of the things that we looked at in order to gather some intelligence on this is measurements that we can collect across our member companies' networks. And here's an example of some data we collected on a North American ISP. This is looking at the packet latency round trip across. This is going from the device in the customer's home through their home network, through the access network, through the ISP's core network, all the way to an interconnect or peering point, and then round trip from that peering point back to the user. And so this is a complementary CDF plot and on a log scale. And you can kind of see the distribution of latency. So latency is highly variable. You see a median value around 18 milliseconds. That's not so bad. But when you start to look at the tail of the distribution going out, let's say the 99th percentile, 200 milliseconds of packet latency across that N10 network. And even farther out in the tail, the 99.9th percentile, so 1 out of 1,000 packets, 1 second of latency or more. So clearly there's some work to be done here. I think the 18 millisecond number probably something that people would consider to be decent latency for game performance. Obviously, smaller is better, but the distribution is seen as 1 out of 100 or 1 out of 1,000 packets having these much higher latency values. That's what we need to solve, and that's what we're here to talk about today. We have a pretty exciting new technology that that we're introducing into the global cable ecosystem. We refer to it as low latency DOCSIS. It's an LLD for short. It's a recent update to the DOCSIS specifications that CableLabs publishes. And it's actually not a new version of DOCSIS. It's not DOCSIS 4 or 5 or anything like that. It's an enhancement that goes directly into the DOCSIS 3.1 specification and then carries forward into future versions as well. And so this was developed as something that can be deployed as a firmware upgrade to existing DOCSIS 3.1 equipment that's in the field today. So cable modems and gateways and equipment that the cable operator deploys in their facilities. It's called the CMTS. And this technology integrates several new features that can dramatically improve the performance for online games and other latency sensitive applications. And the list of kind of names of the features is here. We'll go through some of that in a little bit of detail today and talk about how you can take advantage of it in your applications and make sure that when your customers are on cable networks, how they can get the best experience possible. So the benefits really, we call it low latency DOCSIS, but it's really addressing not just average latency, not just reducing that, but also this variability in latency over time as other applications are sharing the broadband link. So jitter is addressed as well, and then packet loss, particular congestion-related loss that happens in broadband networks today is addressed by LLD as well. So key applications that we think are great candidates to make use of this technology, obviously multiplayer online games, where you're really wanting low loss and stable latency. That's definitely a key thing we've heard that affects gameplay is variability in latency. Cloud gaming as well, which is probably even more sensitive to latency variation, but also throws in the fact that it's much higher throughput than traditional multiplayer online games, where you're sending effectively a video stream to the user rather than just state updates being sent to their console or PC. And then finally, video conferencing is another application today that maybe a little bit less latency sensitive, frankly, than online gaming and cloud gaming, but still obviously latency sensitive and affected by variation in latency and loss as well. So before we get into the details of the technology, I just want to give you a sense for what kind of improvements we're expecting with this new technology. And this table shows two metrics, the average latency and a measure of jitter. One thing about jitter is that there are half a dozen different definitions for what jitter means and how to measure it. Here we're using the 99.9th percentile packet delay variation metric for jitter. And then the table shows 4 different scenarios. The red and yellow are effectively what equipment that's deployed today would experience. So a customer that has existing DOCSIS service or cable broadband service from a cable ISP would be seeing average latencies in kind of the prime time or busy hour of the day around 30 milliseconds or with active queue management 10 milliseconds, and then jitter numbers in the hundreds of milliseconds. So again, corroborating what we saw on that end-to-end slide earlier. This is just looking at the DOCSIS link and seeing its contribution. So clearly a decent chunk of the variation in latency is actually being caused by the broadband link. And so, between the red and the yellow, some cable operators have turned on that active queue management feature in their networks, and so more in the yellow column. Others are probably still in the red column. I think some have it turned on in one direction and not the other today, and so they might be really somewhere in between those two. And then you can see the two columns, green and white, which show the new low latency DOCSIS technology. And you can see the dramatic difference that that can make to the performance of the broadband link. So expectation is, so we had this feature called PGS, or Proactive Grant Service. That's an optional feature that the operator can deploy and turn on a customer by customer basis, and can really get the latency and jitter down to incredibly low numbers. The downside to that is that it's a bit inefficient in terms of upstream bandwidth utilization. And so it does come at a bit of a cost to the operator in terms of their scalability of their network in order to turn that on. We're expecting that that feature is probably most useful for specialized services or maybe high tier customers who where that inefficiency can be justified. But for a mass market deployment, our expectation is more along the lines of that green column. And again, a massive improvement in both latency and jitter compared to what customers are expecting to see today. So what causes all this variation in latency? And as we started looking into this and seeing what we could do to improve latency performance, really honed in on the fact that the biggest source of latency and latency variation and actually loss as well isn't really caused by the network technology. It's actually caused by the traffic that's flowing across that network. And so this isn't actually even specific to cable broadband. It's really a factor that affects all broadband links, all networks, in fact. And it's caused by TCP traffic and other applications like it, or other protocols like it. But the network has a role to play too, in that it's enabling TCP to cause this latency latency and jitter and loss. And the next slide, I'll get into a little bit more. The next couple of slides, I'll get into a little bit more on why that is. One other point on this slide, just to point out, when we talk about latency across networks, the first thing that comes to a lot of people's mind is just the distance across the network and propagation delay that comes as a result of that. Certainly, that's a component. It can be a large component for sure if you're talking about connections that are going beyond continent wide or across continents. That can add up to tens and hundreds of milliseconds on its own. But there's not a whole lot you can do about that, particularly the speed of light piece of that. Distance, some applications can be moved closer to the user. So CDNs are a good example of that, where content can be moved closer to the user. Cloud games are all expected to do similar things, where the gaming servers are located close to the user. But traditional online games, there's a trade-off there, right? You want to have geographic coverage in order to do good matchmaking and get decent populations of users together so that you can have good gameplay. And that aspect of wanting to have more centralized servers that makes it hard to move things close to the user. So let's get into this TCP issue. So TCP and other protocols like it, like QUIC, for example, if you're familiar with QUIC, what they try to do is send data as quickly as they can through the network. And so they use what's called a congestion control algorithm in order to try to probe for the available capacity on the path between the sender and the receiver. And today, nearly all of those algorithms rely on the network to provide fairly deep packet buffers at the bottleneck link in the network between the sender and the receiver, and then drop packets when those buffers overflow. And so what TCP essentially does is fills up that deep buffer in whatever the bottleneck link is, and then to the point where it's dropping packets. And then the TCP connection senses that packets are being dropped and pauses for a little bit to let some of that queue drain out, and then resumes sending faster than that link can support and fills that buffer back up. Now, but there are a lot of applications that don't use TCP. For example, multiplayer online games typically don't use UDP for setting their traffic. But the problem is they get stuck in the same queue and that same buffer. Those packets get stuck in the same buffer as competing TCP traffic does. And so the side effect of this behavior that the TCP protocol has is that all the traffic typically is sharing the same latency, jitter, and loss that is being caused by the TCP traffic. And this isn't constant, right? It as TCP sessions start up and then complete and finish, that those degradations come and go, and so you see really high variability. Things can be great for a long time, and then when a TCP session starts up, the example that Steve gave of a Netflix session which uses TCP starts up and causes the problem. And so where does this happen? It happens, and I mentioned this, at the bottleneck link. So that's the link between the sender and the receiver that has the lowest throughput. And so that's where all this buffering happens. That's where all that latency, jitter, and loss happens. By design, that is typically the access network link. And specifically in the case of cable broadband networks, the access network link is where the service rate is set for the user. So if a user is subscribed to, let's say, 200 megabits per second down by 20 megabits per second up, and that's their service package that they're paying for, that's configured on the cable broadband link, the link between the CM, the cable modem, and the CMTS, or cable modem termination system. So that's where that rate shaping is enforced. That is the bottleneck link. And so that's where all this TCP buffering, latency, loss, and jitter happens. Now, that's not to say that there's never congestion other places in the network. It certainly can be, and we'll talk a little bit more about situations around Wi-Fi in the home network. And sometimes Wi-Fi is the bottleneck, and the client device can't actually fully utilize their cable broadband connection. Sometimes there are bottlenecks other places in the network, in the core or a peer network, or even at the server, that affect things too. But very frequently, it is the broadband link or the Wi-Fi link. So on the DOCSIS link, well, so obviously we have if this situation is occurring in the broadband link, we have an opportunity to fix it. So today, how this works is you've got the cable modem at the customer's home, the CMTS at the cable operator's central office, and you've got these virtual pipes that are configured to provide the service that the customer is subscribed to. All the traffic going downstream to that cable modem goes into a single queue, and whether that's streaming video in this example or a game traffic, it's all going into a single queue. That delay and jitter and loss that the streaming video TCP traffic is causing affects the game packets as well. Same thing happens in the upstream. It wouldn't be a streaming video in the upstream, but instead it might be a speed test or another file upload that is building up latency in the queue in the cable modem, and then all the game traffic is entering that same queue and being subjected to that same variable latency. What we're introducing with this new low latency DOCSIS technology is the ability to have two queues in each direction, two in the CMTS for the downstream traffic, and two in the modem for the upstream traffic. And really just differentiating here between these two categories of traffic. The traffic that are causing latency, the TCP types of traffic that are causing latency and loss, and then the traffic flows that aren't causing latency and loss, and frankly would prefer not to be subjected to it. Give them a separate queue so that they can avoid getting that, having that degradation. So both those queues share the capacity of the service that the customer subscribed to. And this, it's important to note, is just separation or segregation of these two types of traffic. It's not prioritization. It's not trying to identify traffic that is specifically latency sensitive or more important to the user and prioritize that above the other traffic. It's really handled at the same priority level, but just given a separate queue. And so we like to say it's two great queues. One we call the classic queue. The other one we call the low latency queue. It's again, not high priority and low priority. It's not a good queue and a bad queue. Both of the queues are really optimized for the type of traffic that they're carrying, and what we call queue building flows. So those flows that are using TCP, so examples are HTTP and video streaming, bulk data downloads, things like that. They're going to get much better performance in the classic queue than they would in the low latency queue. And so they would prefer to be in that queue. The non-queue building flows, so all those latency sensitive applications that are sending traffic at fairly low data rates and are fairly sparse sending, prefer the low latency queue. So how do we get the traffic into the right queues? The way we've designed this to work is that it's up to the application to decide which queue would work better for it. So in the cable modem and the CMTS, there'll be a default classifier which can identify the non-queue building traffic based on a marking in the IP header of the packet. By default, if that marking isn't present, the packet would go into the classic queue. So there are really two subcategories of traffic and two ways that traffic can be marked to go into the low latency queue. For low data rate flows, the diffserv field in the IP header, which uses a value called a diffserv code point that gets inserted into that field in the IP header. That's what we'll use to classify traffic into the low latency queue. For high data rate flows, for example, cloud gaming and game streaming, that sender would need to implement a technology called L4S, or low latency, low loss scalable throughput. And that's an emerging IETF standard that is compatible with low latency DOCSIS and allows high data rate flows to use that low latency queue and not cause queuing delay. The bottom corner, I've got a couple of links there if you want to look into the IETF work that's going on in this space and how it intersects with this upcoming cable technology. You can Google either of those. Those are the names of the couple of IETF drafts that talk about how this works. So this isn't just a cable technology. We are standardizing it to be used generally across broadband networks. Of course, we anticipate that cable broadband will likely be the first ones to deploy it. Another piece to talk about here is queue protection. So yeah, applications can choose which queue to go in, and they should choose the right one. And those queue building flows wouldn't get any benefit from marking their traffic as non-queue building to try to get into low latency queue. But sometimes things get misconfigured, or maybe there's a malicious application that's trying to cause problems. We have a function that exists in the cable modem and the CMTS that monitors all of the individual flows of traffic or microflows of traffic that are being classified into the low latency queue in each direction, and also monitors the queuing delay in that queue. And if it starts to see a queue building and latency increasing, it identifies the flow or flows that are causing that to happen and starts kicking those packets out into the classic queue. So redirecting those packets to the classic queue. And this is totally based on behavior. It's identifying contribution to latency. It's not based on trying to figure out what the application is or trying to figure out what protocol the application is using. It's just really observing the pattern and the impact that causes on latency. So I gave a table to begin with to show the benefit and kind of in broad terms, but here's a little bit more of an example that shows you more or less in real time kind of what users typically see as different applications stop and are sharing their broadband connection. So this is showing measurements that we did in our lab with two flows, two streams of traffic. One that is marked to go into that low latency queue, and the other one is not marked and goes in the classic queue. The one that goes in the classic queue is the one shown in blue, and the one that goes in the low latency queue is shown in red. And both these flows were modeled after a typical multiplayer online game packet sizes and packet sending patterns, 60 packets per second in each direction. And this is measuring the round trip time over time. So this is almost 2 minutes of gameplay or traffic being sent. And then simultaneously, there was some other traffic going on in the broadband connection. And in particular, you can see in the middle some huge spikes of latency up to 160 milliseconds and then up to 80 milliseconds, a few more. And that's a speed test. So during the middle of this experiment, we started a speed test, and you can see so that's running a whole lot of TCP traffic. You see the impact that causes. The remainder of the time was a mix of other traffic going on that's going across that link and again causing quite a bit of variation. Even when speed test isn't running, you can see the variation, latency spikes up to 50 milliseconds or so. And all that goes away with the traffic that's marked and goes in the low latency queue. And you see the latency variation much, much lower, and the average latency lower as well. So how do you take advantage of this? So as it's up to the application to decide which queue it wants to use, it really is up to the application to opt in for this. So by default, your traffic is going to go in the classic queue, and it's going to get the performance that you saw on the blue graph on the previous slide. But if you mark it as compatible with the low latency queue, if you mark it as non-queue building, then you'll get the benefit of low latency DOCSIS. And so for those high bandwidth applications, again, cloud gaming would be a good example of that. Also, potentially high quality video conferencing apps could use this. That's the L4S functionality that I mentioned earlier. And it involves using the network feedback to adjust the sending rate at the sender in order to avoid causing congestion. And then for the low bandwidth applications, just use the diffserv code point, marking it in the packet header. So just want to kind of wrap up this slide. Again, it's up to the application to select which queue it wants to send its traffic through. That really can be, even within an application, multiple flows of traffic could actually mark their packets differently. So I think there was a question that was provided on the stream asking about could you switch back and forth between the two queues? Absolutely. If you're downloading an asset or uploading an asset, say a recording of gameplay or something like that, or a video that's being served and played to the user, that can absolutely go into the classic queue and get the best performance that way. Meanwhile, the state update packets that are being sent between the game and the server that are those low bandwidth, latency sensitive ones could be marked to go into the low latency queue. That's absolutely the way it should be done. So then I'm going to hand off to Steve to talk about how this interacts with Wi-Fi. So.
Okay, thanks, Greg. So we have a basic assumption as just general users ourselves that Wi-Fi sucks for gamers, and that gamers know this, and no self-respecting gamer would actually play games using Wi-Fi. They're always going to use Ethernet. In our primary research, which is fancy terms for surveys and interviews, we actually found that was not true. We found that 51% of gamers use Wi-Fi always or mostly. When you add in those who use it occasionally, we're up at about 84%. So really, any problems with Wi-Fi are going to basically compound the situation in terms of latency. So if we make the cable link great, but Wi-Fi is still a problem, then we're not really going to have a great solution for people. So here you can see some of the research shows here some of the breakdowns between desktop gamers, laptop gamers, and then console gamers. But you get the clear picture here that gamers use Wi-Fi extensively. So what can we do about that? There's a technology in Wi-Fi called Wi-Fi multimedia, or WMM, sometimes referred to as Wi-Fi QoS or WMM QoS. Really, we're referring to this as low latency Wi-Fi. This technology was introduced about 10 years ago, around the time of 802.11n, and it splits traffic into 4 different categories. Here we have them listed: voice, video, best effort, and background. And that's in descending priority. And this is actually a priority-based system, unlike the DOCSIS technology. We had a theory that we would be able to go in and tweak some of the values that dictate how these different categories are handled, and that would allow us to improve the latency and jitter characteristics of Wi-Fi. When we started that work, we found the simple act of segregating the gaming traffic into the video category from best effort had a massive improvement on both latency and jitter. We went on to do our work to test the tuning and tweaking of the other parameters, and what we found was they made little difference in comparison to this big win, which was separating out the gaming traffic into the video access category. Now, there isn't anything in Wi-Fi per se today to support L4S, but we are looking at how to enhance Wi-Fi to support L4S. I think we've heard of one access point which has started to implement L4S to respect the congestion signaling and to add congestion experienced when it sees congestion in the Wi-Fi traffic.
The mechanism for steering traffic into the different queues is through the differentiated services field of the IP packet
header. So if we look at the next slide,
with just one or two API calls when you're setting up a network socket, you can specify a differentiated services code point for the socket,
is what you expect to see
and from
today,
that point on, all the packets will have that value.
Bundled in with all the other traffic.
With an appropriate choice of code point, the gaming packets
and then if you
will end up in the
identify the
video
gaming
queue
traffic
for Wi-Fi
separately,
and get much better latency and packet drop characteristics.
Here. It's
This
not
packet
quite as marked
marking
an
also
improvement as we
activates
see
the DOCSIS
on
link
the DOCSIS
and puts
link,
the gaming packets
but it's
into the
still
low
a
latency
major
queue there.
improvement in the overall
So we have this great
latency.
symbiotic
the
relationship
average
between the
declines
packet
and the amount of
marking for both
variation
Wi-Fi
declines
and
quite
DOCSIS.
dramatically. Now, we tested this across a wide variety of access points, because one of the things we've seen in some of the gaming forums is that opinions that WMM makes the situation worse, and when people are experiencing terrible latency or jitter on their games, they should turn off WMM. What we found was the reverse was true, that across a wide selection of retail access points, this just improved the situation. It improved it to a greater or lesser extent, depending upon the specific brand and model, but it was a win overall, pretty much across every access point. For L4S, this is a little bit more intrusive, because now if you're developing cloud games, if you're building the infrastructure, you have to start to look at your congestion controller implementation to look at how to respond to the congestion signals, to dial back your rate to make sure you don't overflow the low latency queue or get your packets pushed into the classic queue. So I guess the last thing here
is... Not to say that there aren't some outliers out there But right now,
when will low latency DOCSIS
we think it's a low-risk activity to start doing packet marking and get the benefits of reduced Wi-Fi latency and jitter immediately, and then get the additional latency and jitter benefits of low-latency DOCSIS when the operators roll it out, without any additional work at that point.
You can reasonably expect that
doing this is really easy, taking, as we mentioned, only a couple of extra API calls when setting up a socket, and from that point on, all traffic going out will have that diff-serve code point, and will get the beneficial latency treatment.
To support low latency DOCSIS, and the cable operators are actually working on rollout plans for this now. So with that, that's what we have here. We've got some resources to provide you with some insights. One of the things we've done here is we created basically a landing site called pingspikeskill.com, and that will kind of redirect you out. We have a repo that gives you some code examples to show you how you can implement this in Windows or in Linux, in Android. We're working on a solution, an example for iOS, but it gives you some kind of direct code snippets and insights on how to implement differentiated services marking in your application. It's really very simple. In the case of L4S, there is details. The details here is in the IETF draft, and then CableLabs has a technology primer on how this technology works. The following link on low latency DOCSIS.
Yeah, so and I can just add to that, Steve. That technology primer talks about the dual queue as well as the L4S technology that actually gives an overview of the L4S architecture in case you want a quick easy read on how that works. And also talks about some of the other features which are maybe more specific to cable networks, some of the scheduling services like PGS that I mentioned at the outset, in case you're curious about that. But it's a pretty good overview of the technology in a bit more depth than we were able to go into today. So certainly take a look at that if you're interested.
Okay. Yeah. And one thing to add here, Greg, is that if you don't do this in the application and you basically rely upon your access point to do this, at that point, the traffic has already gone from the PC to the Wi-Fi access point with the default traffic category and the existing latency. So what we need is to get to the point where the applications identify it so that it gets the benefit over the Wi-Fi link as well as getting it over the DOCSIS link. Okay, so that looks like that's all we've got for questions right now. So with that, I'll hand it back to Natalie. Thanks for the opportunity to present on this topic.
Thank you guys so much for everything today. I apologize for the technical difficulties and sorry to those in the audience for those today as well. We'll be working to put this together on YouTube, and if you have any further questions, we'll make sure that both Greg and Steve's emails are available there as well, so you can reach out to them if you have any further questions. Thank you all so much, and I hope you have a great rest of your day.